Fermi National Accelerator Laboratory, located just outside Batavia, Illinois, near Chicago, is a United States Department of Energy national laboratory specializing in high-energy particle physics. Since 2007, Fermilab has been operated by the Fermi Research Alliance, a joint venture of the University of Chicago, Illinois Institute of Technology and the university's Research Association. Fermilab is a part of the Illinois Technology and Research Corridor. Fermilab's Tevatron was a landmark particle accelerator, at 3.9 miles in circumference. It was the world's second-largest energy particle accelerator, until it was shut down in 2011. In 1995, the discovery of the top quark was announced by researchers who used the Tevatron's CDF and DO detectors. In addition to high-energy collider physics, Fermilab hosts smaller fixed-targetum neutrino experiments, such as mini-boona and micro-boona. SBOONA-. The mini-boona detector is a 40-foot diameter sphere that contains 800 tons of mineral oil lined with 1,520 phototube detectors. An estimated 1 million neutrino events are recorded each year. SBOONA is the newest neutrino experiment at Fermilab. It sits in the same neutrino beam as mini-boona but has fine-grained tracking capabilities. The MINUS experiment uses Fermilab's NUMA beam, which is an intense beam of neutrinos that travels 455 miles through the Earth to the Soudan mine in Minnesota. In the public realm, Fermilab hosts many cultural events, not only public science lectures and symposia, but also classical and contemporary music concerts, folk dancing and arts galleries. The site is open from dawn to dusk to visitors who present valid photo identification. Asteroid 11998 Fermilab is named in honor of the laboratory. History: Western Illinois was a community next to Batavia voted out of existence by its village board in 1966 to provide a site for Fermilab. The laboratory was founded in 1967 as the National Accelerator Laboratory. It was renamed in honor of Enrico Fermi in 1974. The laboratory's first director was Robert Rathbun Wilson, under whom the laboratory opened ahead of time and under budget. Many of the sculptures on the site are of his creation. He is the namesake of the site's high-rise laboratory building, whose unique shape has become the symbol for Fermilab and which is the center of activity on the campus. After Wilson stepped down in 1978 to protest the lack of funding for the lab, Leon M. Lederman took on the job. It was under his guidance that the original accelerator was replaced with the Tevatron, an accelerator capable of colliding proton in an antiproton at a combined energy of 1.96 TeV. Lederman stepped down in 1989 and remains Director Emeritus. The Science Education Center at the site was named in his honor. The later directors include John Peoples, 1989 to 1999, Michael S. Witherell, July 1999 to June 2005, Pierre Maria Roduns, July 2005 to July 2013, Nigel Lockyer, September 2013 to the present. Fermilab continues to participate in the work in the LHC. It serves as a Tier 1 site in the worldwide LHC computing grid. Accelerators. Current state as of 2014. The first stage in the acceleration process takes place in two ion sources which turn hydrogen gas into H- ions. The gas is introduced into a container lined with molybdenum electrodes, each a matchbox-sized, oval-shaped cathode and a surrounding anode, separated by 1 mm and held in place by glass ceramic insulators. A magnetron generates a plasma to form the ions near the metal surface. The ions are accelerated by the source to 35 keV matched by low-energy beam transport into the radio frequency quadrupole, which applies a 750 keV electrostatic field, giving the ions their second acceleration. At the exit of RFQ, the beam is matched by medium energy beam transport into the entrance of the linear accelerator. The next stage of acceleration is linear particle accelerator. This stage consists of two segments. The first segment has 5 vacuum vessel for drift tubes, operating at 201 MHz. The second stage has 7 side-coupled cavities, operating at 805 MHz. At the end of LINAC, the particles are accelerated to 400 MeV, or about 70% of the speed of light. Immediately before entering the next accelerator, the H- ions pass through a carbon foil, becoming H+ ions. The resulting protons then enter the booster ring, a 468-meter circumference circular accelerator whose magnets bend beams of protons around a circular path. The protons travel around the booster about 20,000 times in 33 milliseconds, adding energy with each revolution until they leave the booster accelerated to 8 GeV. The final acceleration is applied by the main injector, which is the smaller of the two rings in the last picture below. Completed in 1999. It has become Fermilab's particle switchyard in that it can route protons to any of the experiments installed along the beamlines after accelerating them to 120 GeV. Until 2011, the main injector provided protons to the antiproton ring and the tevatron for further acceleration, but now provides the last push before the particles reach the beamline experiments. 2 ion sources at the center with 2 high-voltage electronics cabinets next to them. Beam direction right to left. RFQ, MEBT, first drift tube LINAC. A 7835 power amplifier that is used at the first stage of LINAC. A 12 MW klystron used at the second stage of LINAC. A cutaway view of the 805 MHz side-couple cavities. Booster ring. Fermilab's accelerator rings. Proton improvement plan in recognizing higher demands of proton beams to support new experiments. Fermilab started an initiative to enhance their accelerators. The project started in 2011 and will continue for many years. The project has 2 phases called Proton Improvement Plan and Proton Improvement Plan 2. PIP. The overall goals of PIP are to increase the repetition rate of the booster beam from 7 Hz to 15 Hz and replace old hardware to increase reliability of the operation. Before the start of the PIP project, a replacement of the pre-accelerator injector was underway. The replacement of almost 40-year-old Cockcroft-Walton generators to RFQ started in 2009 and completed in 2012. At the LINAC stage, the analog beam position monitor modules were replaced with digital boards in 2013. A replacement of LINAC vacuum pumps and related hardware is expected to be completed in 2015. A study on the replacement of 201 MHz drift tubes is still ongoing. At the boosting stage, a major component of the PIP is to upgrade the booster ring to 15 Hz operation. The booster has 19 radio frequency stations. Originally, the booster stations were operating without solid-state drive system, which was acceptable for 7Hz, but not for 15Hz operation. A demonstration project in 2004 converted one of the stations to solid-state drive prior to the PIP project. As part of the project, the remaining stations were successfully converted to solid-state in 2013. Another major part of the PIP project is to refurbish and replace 40-year-old booster cavities. Many cavities have been refurbished and tested to operate at 15 Hz repetition rate. The completion of cavity refurbishment is expected to be completed in 2015, and the repetition rate can be gradually increased to 15 Hz operation from that point. A longer-term upgrade task is to replace the booster cavities with a new design. The research and development of the new cavities is underway. The completion of the booster cavity replacement is expected to be in 2018. PIP-2. The goals of PIP-2 include a plan to deliver 1.2 megawatts of proton beam power from the main injector to the deep underground neutrino experiment. Target at 120 GeV and the power near 1 megawatt at 60 GeV, with a possibility to extend the power to 2 megawatts in the future. The plan should also support the current 8 GeV experiments, including mu2e, G2, and other short baseline neutrino experiments. These require an upgrade to the LINAC to inject to the booster with 800 MeV. The first option is to add 400 MeV afterburner superconducting LINAC at the tail end of the existing 400 MeV. This requires moving the existing LINAC up 50 meters. However, there are many technical issues with this approach. The preferred option is to build a new 800 MeV superconducting LINAC to inject to the booster ring. The new LINAC site will be located on top of a small portion of Tevatron near the booster ring in order to take advantage of existing electrical and water and cryogenic infrastructure. The PIP-2 LINAC will have low-energy beam transport line, radio frequency quadrupole, and medium-energy beam transport line operated at the room temperature with a 162.5 MHz and energy increasing from 0.03 MeV. The first segment of LINAC will be operated at 162.5 MHz and energy increased up to 11 MeV. The second segment of LINAC will be operated at 325 MHz and energy increased up to 177 MeV. The last segment of LINAC will be operated at 650 MHz and will have the final energy level of 800 MeV. Project X. Project X is a long-range plan to bring accelerators at Fermilab campus to new frontiers. The plan for accelerators focuses on two of the three frontiers that are long-term plan of Fermilab. In the intensity frontier, the new high-intensity accelerators will support experiments that require intense particle beam to understand particles such as neutrinos, muons, kaons and nuclei. In the energy frontier, the accelerators will support detection of new particles and forces with potential future projects such as multi-TeV muon collider. The immediate plan of Project X is to focus on the intensity frontier. The project is broken down into 3 stages. Stage 1 includes upgrade to existing facilities to support immediate experiments. This stage has translated into work done in the Proton Improvement Plan. Stage 2 includes delivery of 3 concurrent beam levels. 2.9 megawatts at 3 GeV, 50 to 200 kilowatts at 8 GeV and 2.3 megawatts at 60 to 120 GeV. Stage 3 is to build next-generation accelerators as the front end to the energy frontier based on international collaboration in projects such as Neutrino Factory and Muon Collider. Experiments. Cryogenic Dark Matter Search. COUPP, Chicagoland Observatory for Underground Particle Physics. Dark Energy Survey. Deep Underground Neutrino Experiment, formerly known as Long Baseline Neutrino Experiment. Holometer Interferometer. Mini-Booner. Mini-Booster Neutrino Experiment. Microboon. Micro-Booster Neutrino Experiment. Main Injector Neutrino Oscillation Search. Minor Nu-A. Main Injector Experiment with Nu-S-ONAS. MIPP. Main Injector Particle Production. Mu2e. Muon to Electron Conversion Experiment. Muon G2. No Nu-A. Pneuma off-axis Nu-E appearance. SILHEX. Segmented Large X Baryon Spectrometer Experiment, run to study charmed baryons. Saboon. Sabar Booster Neutrino Experiment. Sequest. Architecture. Fermilab's first director, Wilson, insisted that the site's aesthetic complexion not be marred by a collection of concrete block buildings. The design of the administrative building harkens back to St. Pierre's Cathedral in Beauvais, France. Several of the buildings and sculptures within the Fermilab reservation represent various mathematical constructs as part of their structure. The Archimedean spiral is the defining shape of several pumping stations, as well as the building housing the Minus experiment. The reflecting pond at Wilson Hall also showcases a 32-foot tall hyperbolic obelisk, designed by Wilson. Some of the high-voltage transmission lines carrying power through the laboratory's land are built to echo the Greek letter pi. One can also find structural examples of the DNA double helix spiral and a nod to the geodesic sphere. Wilson's sculptures on the site include Tractricius, a freestanding arrangement of steel tubes near the industrial complex constructed from parts and materials recycled from the Tevatron Collider, and the soaring broken symmetry, which greets those entering the campus via the Pine Street entrance. Crowning the Ramsey Auditorium is a representation of the Mobius strip with a diameter of more than 8 feet. Also scattered about the access roads and village are a massive hydraulic press and old magnetic containment channels, all painted blue. Current developments. Fermilab is dismantling the CDF and DO facilities, and has been approved to continue moving forward with no new G2, and liquid argon test facility. LBNE Fermilab has been approved and currently stands to become the world leader in neutrino physics through its long baseline neutrino experiment. Other leaders are CERN, which leads in accelerator physics with the Large Hadron Collider, and Japan, which has been approved to build and lead the International Linear Collider. Over 350 people from over 60 institutions participate in the long baseline neutrino experiment, working together to plan and develop both the experimental facilities and the physics program. LBNE is expected to be fully constructed and ready for operations in 2022. LBNE plans a world-class program in neutrino physics that will measure fundamental physical parameters to high precision and explore physics beyond the standard model. The measurements LBNE makes will greatly increase our understanding of neutrinos and their role in the universe, thereby better elucidating the nature of matter and antimatter. LBNE will send the world's highest intensity neutrino beam 800 miles through the Earth's mantle to a large detector, a multi-kiloton volume of target material instrumented such that it can record interactions between neutrinos and the target material. Neutrinos are harmless and can pass right through matter, only very rarely colliding with other matter particles. Therefore, no tunnel is needed. The vast majority of the neutrinos will pass through the mantle's material, and in turn, right through the detector. The experiment will thus need to collect data for a decade or two since neutrinos interact so rarely. Fermilab, in Batavia, IL, is the host laboratory and the site of LBNE's future beamline, and the Sanford Underground Research Facility, in Lead, SD, is the site selected to house the massive FAR detector. The term baseline refers to the distance between the neutrino source and the detector. Why neutrinos? Neutrinos, astonishingly abundant yet not well understood, may provide the key to answering some of the most fundamental questions about the nature of our universe. The discovery that neutrinos are not massless, as previously thought, has opened a first crack in the highly successful standard model of particle physics. Neutrinos may play a key role in solving the mystery of how the universe came to consist only of matter rather than antimatter. G-2 Fermilab is continuing an experiment conducted at Brookhaven National Laboratory to measure the anomalous magnetic dipole moment of the muon. The magnetic dipole moment of a charged lepton is very nearly 2. The difference from 2 depends on the lepton, and can be computed quite exactly based on the current standard model of particle physics. Measurements of the electron are in excellent agreement with this computation. The Brookhaven experiment did this measurement for muons, a much more technically difficult measurement due to their short lifetime. Ing detected a tantalizing, but not definitive, 3 sigma discrepancy between the measured value and the computed one. The Brookhaven experiment ended in 2001, but 10 years later Fermilab acquired the equipment, and is working to make a more accurate measurement which will either eliminate the discrepancy or, hopefully, confirm it as an experimentally observable example of physics beyond the standard model. Central to the experiment is a 50-foot diameter superconducting magnet with an exceptionally uniform magnetic field. This was transported, in one piece, from Brookhaven in Long Island, New York, to Fermilab in the summer of 2013. The move traversed 3,200 miles over 35 days, mostly on a barge down the East Coast and up the Mississippi. The magnet was refurbished and powered on in September 2015, and has been confirmed to have the same 69971300000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 As of October 2015, the project is working on shimming the magnet to improve its magnetic field uniformity. This had been done at Brookhaven, but was disturbed by the move and must be redone at Fermilab. Particle discovery on September 3, 2008. The discovery of a new particle, the bottom omega baryon, was announced at the DO experiment of Fermilab. It is made up of two strange quarks and a boson quark. This discovery helps to complete the periodic table of the baryons, and offers insight into how quarks form matter. Wildlife at Fermilab. In 1967, Wilson brought 5 American bison to the site, a bull and 4 cows, and an additional 21 were provided by the Illinois Department of Conservation. Some fearful locals believed at first that the bison were introduced in order to serve as an alarm if and when radiation at the laboratory reached dangerous levels, but they were assured by Fermilab that this claim had no merit. Today, the herd is a popular attraction that draws many visitors, and the grounds are also a sanctuary for other local wildlife populations. Working with the Forest Preserve District of DuPage County, Fermilab has introduced barn owls to selected structures around the grounds.